So in this video, we're going to look at solving linear equations. Those are going to be equations which have variable terms, including a letter like x, as well as constant terms, which are numbers with no letters attached to them. Where we do see the variable terms, those x's or y's or whatever letter we'll be looking at, those variables will not be in any denominators. They will also not have any visible exponents, so it's just going to be the letter with its coefficient and then constant terms. And so when we're solving for these linear equations, what we're solving for is trying to figure out what value of x will make this equation a true statement. What value, what number can I plug in for x that will make the left side actually equal to the right side? And there's going to be four main steps that we take as we solve these linear equations. First, we'll want to distribute, and that's where we will get rid of parentheses. Sometimes they trap x inside the equation, so we'll use distribution to release x from those parentheses. Sometimes we'll need to simplify either side of the equation just to kind of clean things up a bit. We may need to relocate terms where we'll put letters on the left side of the equal sign, numbers on the right side of the equal sign. And then our last step will be to isolate the variable, which means to totally get the letter completely by itself and to solve for it. So for this particular equation I have here, I do see terms with constants and I see terms with variables. I'll go through my to-do list, and some of these steps I won't need to do, some of them I will. So step one, distribute. I have nothing to distribute here because I have no parentheses. So I'll go to step two, where I simplify each side of the equation. In this case, it'd be like combining like terms. So if I look at the left side, I have a variable term and a constant term, but they're not like, so I can't combine them together. And that same is true for the right side of the equation. I have a constant term and a variable term. Since they're not like terms, I can't combine them. So simplifying, nothing to do there. Next comes the relocation step, and so this is the big step where we start moving things around. And anytime you relocate terms in an equation, you're going to either use addition or subtraction to move things from one side to the other. Let's focus on one thing at a time. Let's first focus on our variables. Let's focus on moving the letters to the left. So this 15x, I like it because it's on the left side of the equals, but this 9x I don't like. It's on the right side. Let's put it over on the left. Because it is currently a positive, what I'm going to do is I'm going to subtract that 9x to remove it from the right side. And I can see if I had 9x minus 9x, it's now gone. It's no longer on the right side, but it's only legal to do this if I do the exact same thing on the other side. I have to maintain the balance of the equation. So if I'm subtracting 9x from the right, then I need to subtract 9x from the left as well. And while we're at it, let's also relocate our constants. This constant 10 is on the right, and that's where I want him, but my constant 8 is on the left. Let's relocate him to the right side. 8 right now is a negative. To relocate him, I will add. So anytime I relocate something to the other side of the equation, I either add or subtract, and it's always the opposite sign. So when I subtract over here the 15x minus the 9x, I'm going to wind up with 6x. Notice that the negative 8 that I now add 8 to, it's now gone. 8 is no longer on the left side. Then I have my equals. For my constants, I have 10 plus 8, which gives me 18. And then notice these variables also cancel out. 9x minus 9x is now gone. And so what I've done by moving things around, by adding the same thing to both sides or subtracting the same thing from both sides, maintaining that balance, I've now moved everything with a letter to the left and everything that's just a constant to the right. And so now I'm in that last step of isolate. I want the x totally by itself. I want to know what does x equal. Right now there's a 6 attached to that x, and as a coefficient it is attached with multiplication. We're going to detach it with division. So as you're moving things around and detaching things, you're always going to use the opposite operation. So again, where we had addition, we subtract. Where we had subtraction, we add. Where we had multiplication, we now divide. We always use the opposite operation. And so 6x divided by 6 is just x equals, and then 18 divided by 6, we get 3. And we now see that x equals 3. And what that tells me is that back in the original equation, in that original statement, had I put a 3 where I saw the x's originally, this equation would have given me a true statement. So for example, if I plugged in a 3 here, 15 times 3 is 45. 45 minus 8 would be 37 would have been on the left-hand side of the equal sign. And if I plugged in 3 over here, 9 times 3 is 27, and that plus this 10 is 37. And so that's a way of making the left side equal the right side. If I plugged anything else in for x, it wouldn't be true. It would come out to be a false statement. So what we're doing when we're solving equations is we're trying to find the truth. We're trying to find what does x need to be to make the left and the right equal to each other. So here's our solution. We can go ahead and box it. X does equal 3. But I do want to emphasize another way that we can write our solutions. It's fine to say x equals 3, but sometimes you're going to be looking for what's called the solution set. And in math, a set is really just a collection. So if they ask for a solution set in your online homework, they're asking for the collection of all possible answers. And there's a special notation we use for set notation. To describe a set in math language, we use curly braces. And in those curly braces, we put any and all solutions that will work. In this case, the only solution that was found was 3, and so in these curly braces, I will put that solution of 3, and so this would be my solution set. It's the collection of all answers, and again, I use these braces to show that collection, to show that set. So I've got my solution of 3, and I've got my set notation. So let's take a look at another example. Maybe make things a little bit more complicated. See if we can tack on some additional steps. All right, let's look at 4x plus 3 on the left, and on the right, we'll have negative 3 plus 2x plus 16. So again, we'll go through our 4 steps. First step is to distribute, and that's to remove parentheses if there are any, but here there aren't. And so I'll just skip the distribution piece. Step 2 is I want to simplify. I want the left side to be as clean as it can be, and I want the right side to be as clean as it can be, so I'm looking for a way that I can combine like terms if possible. Now on the left side, there are no like terms. I've got a variable term and a constant term. They're not alike, so I leave them separate. But on the right side of the equals, I do have a variable term, but then I have 2 different constant terms. Those guys can go ahead and combine. So on the left, I won't touch it. It's just going to stay that 4x plus 3. I could not combine any terms there. But on the right side, I have the 2x, which is the only variable term that was there. But then I can take that negative 3 plus that 16 and get 13 as my combined constant. And so now each side is about as cleaned up as I can make it. Now comes the fun part. Now is where we relocate terms. So I'm going to put my letters on the left. So the 4x is fine where he's at, but the 2x needs to move. Right now, he's technically a positive 2x. So using that opposite operation idea, I'm going to take that plus 2x, and I'm actually going to subtract 2x from that side. But I am only allowed to do it if I maintain the balance by doing the exact same thing on the other side. So I'm going to be removing the 2x from the right, pushing it to the left. I'll do the same thing with the constants. I want my letters on the left, but I want my constants to move to the right. So that 3 was currently a positive. I'm going to remove him with subtraction, which is fine as long as I do the exact same thing on the other side. And so now on the left, 4x minus 2x gives me 2x. The 3 minus 3 cancels it out, it's gone. 2x minus 2x, gone. 13 minus 3 gives me 10. So I've successfully moved all the letters to the left and all the numbers to the right. So variables left and constants right. And now I'm on my last step. I need to isolate, meaning I need to get that x totally by itself. Right now there's a 2 attached to it. It is attached with multiplication. So I'm going to detach it by dividing. And it's fine to do that as long as I do the exact same thing to both sides to, again, maintain that balance of the equation. So on the left, 2x divided by 2 is x. On the right, 10 divided by 2 will give me 5. And so my solution is the x equals 5. But again, in your homework, you might be asked to write the solution set. And anytime they use that word set in math, they're talking about those curly braces. So if I were to look at the set notation for this answer here, again, the set means I'm looking at the curly braces, and those braces are like the container that holds my collection of answers. My only answer is 5 though, so in this container, I'll just put that one solution of 5. So I've got my solution that x is 5, that's the value x needs to be to make the left side actually equal the right. And this is just that fancy way that we can say it as a set notation. Here's the collection of all answers. We use those curly braces just to say set in math language. So there's another example. Let's try a third example where this time we get to use all of our steps, including the distribution piece, because we love to distribute. It's so fun. So let's see here. Here we've got 8 minus 2 times the quantity x plus 1 is equal to x plus 9. So in this example, we can see that there are, again, lots of x's, lots of numbers, but this time x is trapped in a parenthetical prison. It's trapped in parentheses. And so what we need to do, if we're trying to eventually get x by itself, if we have to isolate it, if it's trapped, we got to release it. So step 1, we are going to distribute to remove these parentheses. So that negative 2 is going to get multiplied to x as well as 1. So we will have the 8, which was originally there. Negative 2 times x is negative 2x. Negative 2 times positive 1 is negative 2. And then on the right side, no distribution to do. I see no parentheses there, so we're good. All right, so there was step 1, getting those parentheses out of there by distributing. Next comes the simplifying. We just want things to be as clean as we can get them. So on the left, notice that we do have 2 constant terms that we can combine. We then have this negative 2x as the only variable term that was on that left side, but the 8 minus 2 combine to give us 6. On the right side, I have no like terms. The letter and the number don't combine, so we leave them separate. So I have removed the parentheses, I've combined like terms, and now I want to relocate. This is the fun step. So we're going to push those letters to the left. We're going to move the numbers to the right. So for our letters, I'm going to take this positive x, and to remove it and relocate it, I'm going to do the opposite sign. I'm going to subtract the x from both sides. And while we're at it, let's relocate the constants. I want all my numbers to move to the right, so this positive 6 will relocate by subtracting. And again, it's always fair to do the adding and subtracting. As long as you do the same thing to both sides, you want to maintain that balance. So on the left, we have negative 2x minus 1x. That gives us negative 3x. 6 minus 6 is gone. We have the equal sign. X minus x, gone. 9 minus 6 is 3. And so we have successfully relocated letters to the left and numbers to the right. And we're in that last step now where we want to isolate, we want to get the x totally by itself. Right now there's a negative 3 attached to it. It's attached with multiplication, so we're going to detach it with division, always using that opposite operation. And it's safe as long as I do the exact same thing to both sides to maintain that balance. So now on the left, negative 3x divided by negative 3 is a positive 1x. And on the right, 3 divided by negative 3 is a negative 1. And so now I have my solution, x equals negative 1. But again, in your computer program, they might be asking you for that solution set. And so if they're asking for that set notation, again, you can think set is just those curly braces to say, here's my collection of possible answers. We only had one possible answer, and that was negative 1, so I'll put that in my set notation. All right, let's try some more where we can distribute again. Okay. I like distributing so much, I'm going to pick one where I can do it twice. So here I've got negative 12 on the left. Left is nice and clean, But on the right, I've got 7 times the quantity 2x minus 3 minus the quantity 8x minus 9. Okay. Now we got to be careful here. These parentheses are very close to each other, but they are not getting multiplied, they are being subtracted. So what you may want to do is to write the invisible implied coefficient that's really there. So what I need to do is distribute 7 into these parentheses here, 7 times 2x and 7 times negative 3. But then I'm taking this negative 1 and distributing it into the 8x and the negative 9. So just be really careful. If there's a subtraction or an addition sign between your parentheses, you're not foiling, you're not doing distribution with the 2 sets of parentheses. It's just the negative 1 that's coming in here, just as the 7 comes in there. So let's see what happens when we distribute. The left side's nice and easy, nothing to do there, it's just a negative 12 again. But on the right, 7 times 2x gives us 14x. 7 times negative 3 gives us negative 21. Negative 1 times 8x gives us negative 8x. And negative 1 times negative 9 gives us positive 9. So we've done our distribution, that's step 1. We've released x from the parentheses. So now they're free to move around. But before we do the relocation, let's simplify. Let's just keep things as clean as we can make them. Now the left is already clean. I can't get easier than negative 12. But on the right, I've got some cleaning up to do. On the right, I have some like terms with x's, and I have some like terms that are constant. So I'm going to leave my left alone. On the right, let's look at our variable terms. If I have 14x minus 8x, that's going to leave me with 6x. If I have negative 21 plus 9, that's going to leave me with negative 12. So now I've got all the parentheses gone, and I've combined my like terms, cleaned things up a bit. Now my job is to relocate. I want letters on one side, numbers on the other. Now here's the deal. I like to say let's put the letters on the left, and it's going to help a lot when we get to the inequalities in the next video. But technically it doesn't matter what side the letters or the numbers go on. It really doesn't matter. The idea is that you want x's on one side, numbers on the other. But knowing where we're going with inequalities, I would still suggest trying to make that habit of putting letters on the left and constants on the right. So even though this is going to make me move stuff more than I really need to move stuff, I'm going to go ahead and move my x. I don't like him on the right. I'm going to take that positive x and I'm going to subtract it, which is fine as long as I do it to both sides. Now I'm not going to have a whole lot of room over here to do this, but there's going to be a minus x happening on both sides. And while I'm at it, let's move those constants to the right. So this negative 12, let's add that 12 to both sides to get it to relocate. And so on the left side, I didn't have any x's to begin with, so if I had nothing and I subtracted 6x, I now have a negative 6x over here. The negative 12 plus 12 is now gone. Equals, the 6x minus 6x is now gone. And interestingly, the negative 12 plus 12 is gone. Now I can't just have the right side be blank, so when I say it's gone, what I'm saying is that these are canceling each other out. Negative 12 plus 12 is just 0. So we've got negative 6x on one side, we've got 0 on the other. So I've done my distribution, I've done my simplifying by combining like terms, I've relocated letters to the left and numbers to the right, and now I need to isolate. So right now I've got a negative 6 attached to the x, I want to detach it with division. So I'm going to divide both sides by negative 6. Negative 6x divided by negative 6 is x by itself. 0 divided by negative 6 is 0. And so my answer is that x must equal 0. So that means if I had plugged in a 0 everywhere I saw an x here, then this right side would eventually say negative 12 if I started cranking stuff out. And again, if I was looking for that set notation, Or if the directions are saying write the solution set, anytime they use that word set, they're looking for these curly braces just to show the container that holds all of your possible solutions. We have a solution of 0, so there is my solution set, or my set notation. All right. Now, so far the examples I've shown you have pretty nice answers. They have whole number answers. Sometimes they're positive, sometimes they're negative, sometimes they're 0. But life isn't always that nice. Sometimes we have solutions that turn out to be fractions. So let's take a look at a couple of those and see how to deal with them. The nice thing is, when your answers are fraction, you just have to box it and say, okay, I'm done. I don't have to do anything with it. So if you have a fear of fractions, don't worry as we go through these. The process is exactly the same. You don't actually have to work with the fractions. You just wind up with them. Okay. So let's take a look at this one. Again, we want to go through those same 4 steps. We want to distribute to get rid of parentheses. We want to clean things up by combining like terms. We want to relocate letters to one side, numbers to the other, and then isolate to get the x by itself. So first we will distribute. We want to get rid of these parentheses. So 5 is going to get multiplied to both of those terms. 5 times 2x will be 10x. 5 times the negative 1 is negative 5. And I don't see any other distribution to do. I'm just going to copy everything else exactly as is. So there's our distribution. Parentheses are gone. Everyone's free to move around. So before we start relocating, let's clean things up a bit. On the left side, I do see like terms, the 10x and the negative 6x. I can go ahead and combine those together. 10x minus 6x will give me 4x. I still have that minus 5. And then I still have the 1 on the right side. So I've distributed to get rid of parentheses, I've combined my like terms together, and now I get to relocate. So I want my letters on the left and my numbers on the right. Letters are already on the left. There's only one variable term in the whole equation now, and that's the 4x, so I'm going to leave him where he's at. But the constant, negative 5, I'm going to relocate him to the other side. And again, whatever his sign is, in this case it was a negative sign, I'm going to use the opposite. So when I relocate, I either add or subtract. I'm going to use the opposite sign to relocate him. So now I've got 4x on the left, and then negative 5 plus 5 cancels away. This is now equal to 1 plus 5, which is 6. So I've got my letters on the left, my numbers on the right. My last step is to isolate. I want to get the x totally by itself. Right now there's a 4 attached to it with multiplication. I'll detach it with division, and that's fine as long as I do the same thing to both sides. So now 4x divided by 4 is just x. But 6 divided by 4 is not a whole number. So this is different than the last examples we looked at. 6 divided by 4 is not perfect. But here's the deal. If I do have a fraction, I do want to write it as a simplified fraction. So look at the numerator and denominator and ask, is there a GCF that they share that would indicate this can reduce? So when I look at the 6 and the 4, do they have a common factor that goes into both? And I see a 2 that goes into 6 and it also goes into 4. So this fraction can reduce. If I imagine dividing 6 by 2, 2 goes into 6 3 times. 2 goes into 4 twice. And so my reduced fraction would be the fraction 3 over 2. And I'm going to leave it as an improper fraction. I don't want to change it to 1 1/2. I don't want to change it to 1.5. I'm going to leave it just like that. I know that this is simplified because the GCF of 3 and 2 is just 1. Nothing will go into 3 and 2 except for 1. So there's my solution. Like I said, you don't have to be scared that it's a fraction, because as I was going through this process, it was the same work as we've been doing. It's just a coincidence that at the end we have a fraction that we box as our answer. And again, if we had to write that set notation, again, we're just looking for those braces to indicate the collection of all answers. In this case, the answer that we can include in that set is 3 over 2. So see, fractions don't have to be too scary at all. Let's take a look at another one where again, we will push our limits with some fraction answers. We know it's not scary. So here I've got 5x plus 2 times the quantity x minus 6. And then on the right side, we'll have 4 times the quantity x plus 1 minus 2. This one's going to be fun because this one has 2 distributions to do, lots of combining like terms, and in the end we get a super fun fraction for our answer. So let's see how it goes. Step 1, we want to distribute. We want to get everything loose to be able to move around, so we will distribute the 2 inside this set of parentheses here. We'll distribute the 4 into this set of parentheses here. So on the left, we've got the 5x that was originally there. Then we've got 2 times x, that'll be 2x. We have 2 times negative 6, that'll be negative 12. And then on the right side, 4 times x is 4x, and 4 times 1 is 4, and then again, copy anything else that needs to be copied. So there's our distribution. All the parentheses are now gone and everyone's free to move around. Before we relocate though, let's kind of clean things up. So on the left side, I see my like terms that I can combine. 5x plus 2x will give me 7x. And then I have the minus 12. On the right side, there's nothing like the 4x. There's no other variable term. But the 4 and the negative 2 can combine. So 4 minus 2 will give me positive 2. So I've gotten rid of my parentheses, I've cleaned things up a bit, and now I hit my relocation step. So I'm going to relocate my letters to the left and my constants to the right. So my x, which is currently a positive 4x, I will relocate him to the left using subtraction. Again, always that opposite sign when you relocate. And then for the constant numbers, I've got negative 12 that I'd like to relocate. I'll use addition to relocate that negative. So adding 12 to both sides. And so now on the left, I have 7x minus 4x. That gives me 3x. Negative 12 plus 12 is gone. On the right, 4x minus 4x is gone. 2 plus 12 is 14. And so we've successfully relocated letters to the left, numbers to the right, and our last step now is to isolate. I see that 3 is attached to the x using multiplication, so I'm going to detach it with division, which is fine as long as I do the same thing to both sides. So 3x divided by 3 is x, and then on the right side, 14 divided by 3 is not going to be nice. It is going to be a fraction, but we do want to make sure it's a reduced fraction, so let's just double check this one. Look for the GCF between the top and bottom. So between 14 and 3, what number goes into both? And in this particular case, nothing goes into both except for 1. 1 is the GCF, and so I know that that is a simplified fraction. So my solution here is the 14 over the 3. And again, if I wanted to write that set notation, oh dear, I want to write that set notation. It's just that fancy way of saying, let's use braces to describe my collection of answers. In this case, it's the 14 over 3. All right, so those are 6 examples that are kind of straightforward. We had examples where we had whole numbers, we had examples with fractions, sometimes they were negative, sometimes positive, sometimes 0. But I've got 2 more examples I want to show you that are special cases. And see what we think of that. Let's see here, these are going to be interesting. Let's take a look at 4 times the quantity 3x plus 2 equals 12x plus 8. So again, we have our same 4-step procedure. Step 1, we want to get rid of parentheses. We want to make things loose to move around. So we are going to distribute the 4 inside those parentheses there. And we get 12x plus 8. And then we'll copy the rest. And at that point, you scratch your head and you go, okay, so the left side says 12x plus 8, the right side says 12x plus 8, and this is telling me that 12x plus 8 is the same as 12x plus 8. And you go, yeah, that's true, I know that. This is the same as that, yes. Let's say that we're taking a test though and we're not necessarily thinking straight. Let's say that we're not very observant and we don't notice that, that obvious this is the same as that. Let's just go through the motions. We just distributed, so there's no parentheses. I can't clean anything up because on the left side and as well as on the right, there are no like terms to combine. Let's try relocating and just see what happens. If I relocate letters to the left and numbers to the right. So over here I have a 12x I'd like to scoot away. Currently this 12x is positive, so to relocate him I will subtract 12x. And that's fine as long as I do it to both sides. At the same time, let's deal with that constant. I want the numbers to move to the right. So this positive 8 can relocate if I subtract him, as long as I do it to both sides. Again, I want to maintain that balance. Whatever I do to one side, I do to the other. So now, on the left, 12x minus 12x is gone, and 8 minus 8 is gone. And when I say gone, I mean they're canceling each other out, but like we saw before, I can't just say that the left side's blank. So what I'll say is, well, if all this cancels out, it gives me a 0. There's nothing over there. And then I have the equals. Let's see what's on the right. 12x minus 12x is gone, and 8 minus 8 is gone. And so again, these are canceling out, leaving me with nothing but a 0. And this is now different than if you looked back a few examples, we had a solution where it turned out to say x equals 0. And that was telling me what x equaled. This isn't telling me what x equals. This is telling me that 0 is 0. And I know that 0 is the same as 0. So what does this mean? Well, the fact that x disappeared when we were trying to solve for it, when we were trying to find out what does x equal to make this thing true, if x drops out, what that means is that x doesn't matter at all. It doesn't matter what x is. Regardless of what x is, you're going to have a statement that's similar to this type of statement. So let's just take a look at that statement and see what we can gather from it. If I told you that 0 was 0, if I told you 0 equals 0, you would say, I know, this is a true statement. In math, we have a special name for statements which are true like this. We call it an identity. An identity is a statement that is always true no matter what. And so 0 is equal to 0 no matter what. And if x is gone, it says, I don't care what x is. It doesn't matter what x is. This will always be a true statement. And so when we're solving equations and we're trying to find what does x need to be to make this true, we're trying to find that truth, this is saying, who the heck cares what x is? It goes away eventually. It doesn't really matter in the end. We'll always see truth. We'll always have truth. No matter what x is, this equation's always true. And so I don't care what x is. It could be absolutely anything and I'll always have a true statement. And so in this case, I would say that x could be all real numbers. I could plug in 0 and it would work. I could plug in a positive whole number, a negative whole number, a fraction, a square root of some kind. I can plug in all sorts of numbers. Anything will plug in here and ultimately result in a true statement because it doesn't matter what x is, it eventually goes away. So we could plug in anything. There's all real numbers that would work. Now if you were being asked for set notation, there's two different ways you can do this. To say all real numbers in set notation, you can just use the braces to say the set of, and then just write all real numbers inside it. So again, those curly braces just say here is the set of, or the collection of, and you're saying all real numbers belong in that collection. But math people are kind of lazy, and so we come up with symbols to say all of that. We don't like to write all of that stuff. So instead of saying the set of all real numbers, we can use a symbol that just looks like a fancy looking R. That R says the exact same thing as this. It says the set of all real numbers. So that's an interesting example because the x's disappeared and the constants disappeared and we had a true statement that was true no matter what. So any real number would make this true because it was always going to be true. So I bet you can guess what's coming next. What happens if things are always false. So this was an example where we had truth no matter what. Let's look at an example where we have false no matter what. All right, last example here. Last example. We've got 2 times the quantity x plus 3 minus 5 is equal to 5x minus 3 times the quantity x plus 1. Now I'm giving you the heads up that this is going to be false no matter what, but you know what? You don't need to know that on the onset because you're still going to go through the same 4 steps. You're going to go through the motions. So as we go through the motions, let's distribute. Let's get rid of those parentheses. We want x to be loose. We want everything to be free to move around. So let's distribute. On the left we have 2 times x, which is 2x. 2 times 3, which is 6. We'll copy all this stuff. And then for this distribution, negative 3 times x is negative 3x. Negative 3 times 1 is negative 3. So we've gotten rid of the parentheses. Now we need to combine our like terms. So on the left side, I've got the 2x, which is the only x over there. So I'll just copy him. But then I've got, for my constants, I have 2. Let's combine them. 6 minus 5 would give us 1. And then on the right side, same idea, we want to combine our like terms. In this case, I have 5x minus 3x to give me 2x. And then I'll copy my minus 3. And you might notice something at this point. If these are supposed to be equal and these parts are equal, it's interesting that those other parts aren't equal. Let's see what happens though. We're not going to pretend like we notice anything at all. And we might not notice anything right now. Let's just go through the motions. So we did distribute. We did simplify. Let's relocate. So let's put our letters to the left. This positive 2x, I want to subtract to relocate him to the other side. And for my numbers, I want to take that positive 1 and subtract it to relocate it to the other side. So on the left, 2x minus 2x, gone. 1 minus 1, gone. If everything's gone, you've got 0 on the left side. So now on the right side, 2x minus 2x, gone. Negative 3 minus 1 is negative 4. This is not telling me that x is negative 4. This is telling me that 0 is negative 4. And if I told you that 0, well, that's just the same thing as negative 4, you'd say, no, it's not. 0 is different from negative 4. So this right here is what I would call a false statement. It is not true that 0 is the same thing as negative 4. We call that, in fancy math talk, a contradiction. And again, we see that x has completely vanished from the equation altogether. And again, if x is going away, it means x plays no part in this equation. It doesn't matter what x is. It matters not a lick. So if x doesn't matter, and no matter what x is, we end up with a statement kind of like this, something that's false, something that's not true. Well, the whole point of solving an equation is to figure out what x needs to be to make it true. Tell me what x needs to be to make this thing true. Well, this is saying I don't care what x is, no matter what x is, this will always be false. It will never lead to truth. If this is going to lead to false, no matter what x is, there is no x that will make this true. Every x will make this false. And so for this one, there is no solution. There is no solution to this problem. There is no value of x that will ever make 0 equal to negative 4. That's never going to be true. No value will work. And if you're doing set notation, there's a couple different ways. So again, with the set notation, we like to look at those curly braces. Those curly braces tell me the set of or the collection of. Now here's the deal. What I'm supposed to put in those braces is all of the answers that will work. But if we found no answers at all, no solutions at all, then I can't put anything in here. And so I just leave it empty. We call it an empty set. And there's, you guessed it, a special symbol for it. It's a 0 with a slash through it. It says there is no answer at all. It's not actually 0 as an answer. It's no answers whatsoever. Not even 0 will work. Nothing works at all. I have nothing in my collection of answers. no solution. So that's another just kind of funky example. So you've seen infinitely many answers where every real number works. Here's an example where nothing works at all. Most of the time though, you're gonna get one answer. It might be positive, it might be negative, it might be a whole number, it might be a fraction, who the heck cares? But we're always gonna go through, whether it's a special case or a normal case, we'll always go through those same steps. We distribute to loosen things up. We clean things up by simplifying, we relocate so that letters are on one side, numbers are on the other, and then we finish it out by isolating to figure out what the x needs to be to make the equation true, to make the balance happen.